I don't think I need to convince anyone when I say that the coronavirus disease of 2019 is an urgent global issue. The causative agent of the disease is the severe acute respiratory syndrome coronavirus, and currently, in September 2020, there are still no approved antivirals against this virus. Essential to the viral virulence, or its capacity to infect us, is a cysteine protease called Mpro. It's essential because when the virus gets into the cell, it translates the polyprotein, and this protease is the main one to cleave the polyprotein to all the proteins that are required for viral function. It achieves cleavage with a cysteine-histidine dyad. Here, I've included a picture of its substrate binding site where you can see the cysteine and histidine that are essential for catalysis. Since we don't have a protease homologous to this one in the human body, this is a great target for drug development and the reason I have chosen to study it this summer. Of course, considering the global urgency, there's been a lot of research to target this protease. Most of the research have been repurposing already approved antivirals and virtual screening of large compound databases. This latter one is my approach. However, I still consider it unique, and here is why. Essentially, what I have done is identified natural products that are potential covalent inhibitors of the protease. I've taken an interest in covalent inhibition because these inhibitors are more specific and potent, which means that there are less chances of side effects, toxicity, and a smaller dose is required. I've also taken an interest in natural products as these covalent inhibitors because natural products have been useful therapeutic agents for thousands of years. In fact, many of them were discovered by accident, and it was found later that they have a covalent inhibition mechanism. Great examples that demonstrate the utility of natural products as covalent inhibitors are penicillin and aspirin. To do this, I first started by finding covalent warheads in the literature that have previously shown to be capable of cysteine covalent modification. I've shown these here in the slide on the bottom left. Then I extracted all compounds that contain these warheads from the Natural Product Atlas and the Drugbank database, and then I screened them against the protease. For this, I used Molsoft's internal coordinate mechanics software, which takes into account covalent inhibition. Over the thousands of compounds screened, I found 2 hits, which I've shown here on the slide. Both these compounds contain the acrylamide covalent warhead, which is circled in red. The compounds I have identified have higher binding free energy than covalent inhibitors optimized in vitro and reported in the literature. Therefore, as these acrylamide-containing compounds have already been isolated and characterized, in vitro studies are an easy future step.